My name's Melissa. I'm a recent master's graduate out of Dr. Byron Gates' lab at SFU, and I'm here to talk to you today about some more nice fundamental chemistry approaches to things, which is a little different than what we've seen already today. So to begin, I just wanted to talk about the importance of surface chemistry because that's something that we are studying and really interested in. And there are so many different ways that you can functionalize a nanoparticle surface. Nanoparticles are great because they have that really large surface area to volume ratio, so they've got a lot of surface area that you can take advantage of. Whether you want to attach something for targeting purposes, for tracking cells, you want to attach some antibodies to target specific areas in the body, whether you'd like to stabilize these particles long term. This might not work in. Is that better? No. Is that now better? Okay, good. Okay, great. So as I was mentioning, there's many applications and many different things you can do with surfaces. So some applications of iron oxide nanoparticles, which we have seen today, are for use in MRI contrasting. So you can inject them and get better resolution in your MRI images, and they're less toxic than their traditional counterparts. As well, they can be used for other things such as cleaning up oil spills in water by including them in hydrophobic polymers and using that to absorb oil spills on water surfaces, and then you simply take an external magnet and remove them out and the oil comes with, so it's great for cleanup remedies. And then another local example is the use of iron oxide nanoparticles at stem cell, where they use iron oxide nanoparticles to magnetically separate specific cell types out of cell media. So iron oxide nanoparticles are a great core material to use for these studies. And this takes us to the silyl alcohol condensation, which I'll be demonstrating my work on today. But this has been performed in our group in the past, and it is a great advantage over using silane reagents, which are more commonly used. Silanes suffer from the moisture sensitivity that they have, and they must be worked up in a glove box oftentimes. And they're really difficult to manage and reproduce the results of. They can create islands on nanoparticle surfaces, which are ununiform, and that makes the additional steps after the functionalization much harder. So what we've demonstrated in the past is iron oxide nanoparticles coated with a thin layer of silica, where we then do a silyl alcohol condensation reaction with the silyl groups available on the silica surface. And this way we can attach a variety of different functional groups. In the case of the work on the left, thiol-terminated reagents were used, and the gold sulfur attraction was used to attach small gold nanoparticles onto the surfaces of these functionalized particles to more visually demonstrate that our surface chemistry was successful. As well, this approach has been used on lithium niobate nanoparticles, also coated with a thin layer of silica. And from that, we were able to produce these particles that could be used for bioimaging probes, and EDC NHS coupling could be done, and many other different types of surface functionalizations. So it's a really good template. It's low cost, easy to perform, and doesn't take up many resources compared to some other types of reactions. So here's kind of a synthetic method describing what I did in this work. And I kind of zoom in on what's happening on the surface of the nanoparticles. So we've synthesized all of the materials ourselves, starting with the core material, which is approximately 200 nanometer in diameter iron oxide nanoparticles, and they're quite monodispersed, so they're really nice to work with and easy to approximate their surface area. We then coat them with a thin layer of approximately 70 nanometers of silica on the exterior so that we have those silyl groups available. And this thin layer of silica still allows for the magnetic and thermal properties of these core materials to be used in further processes. Then we do the silyl alcohol condensation at an elevated temperature of 80 degrees and attach functional molecules. So the ones that I used for this dual functionalization that I'll show to you today were thiol-terminated and carboxylic acid terminated. And to quantify things, because one step that's often missed with surface chemistry is quantification versus qualification. So what we did here was we used the Ellman's reagent, which is a well-known type of assay used in biomedical type studies. And what happens is that the dithiobis 2-nitrobenzoic acid, the DT and B, can form disulfide bonds with sulfur and thiol groups in solution. Since we have these thiol-terminated structures on the exterior, we could employ this assay, which then releases its counterproduct, which is bright yellow and can be assayed at 412 nanometers with simply UV vis. And that allowed us to do some quantitative work. So what we could determine was the parking area of the functional groups that we loaded onto the nanoparticle surfaces in units of thiols per nanometer squared. And what we want to show here was a control reaction to show that the elevated temperature was necessary to drive this reaction and produce the condensation. So you'll see the control sample here, and all these are performed in triplicate, had very low loading and was likely just due to surface adsorption. So all of the same processes were followed for both samples, except for one was heated at 80 degrees Celsius using conductive heating with a traditional oil bath. So really simple setup. But a long time for each. 24 hours is a long time to wait for one functionalization reaction. But these were the results we found, and this is what was carried out in work previously. So then we took an idea of using microwave heating to speed up this reaction. And since the energy transfer with microwave heating is much more efficient than with conductive heating, we thought this might be a good approach to speed up this reaction and make scaling this up much easier. So usually in conductive heating, you're heating the exterior of your vessel, and then it is heating the materials inside, and that is passing through, but it might not be the most homogeneous environment, whereas microwave heating can induce these superheating pockets within the sample and make for more homogeneous heating throughout. So in a previous work done by a colleague, they determined that they could use microwave radiation to assist in the preparation of self-assembled monolayers on silicon oxide surfaces. And they found that when they used microwave radiation to drive this reaction, they've produced really uniform self-assembled monolayers, and that was the inspiration for performing that type of heating process on these nanoparticles now. So after doing that, we attempted to perform the exact same reaction. We're attaching these thiol groups onto the exterior of these iron oxide silica-coated nanoparticles, and we found that in 1/12 of the reaction time, we were able to achieve similar loading, and that's shown in the center. So both reactions were carried out at 80 degrees Celsius. However, one was in a fraction of the amount of time and still had comparable loading. And there is a third data point there. It's just very, very exactly behind the other one. So we did have good results from this, and we thought we would carry this forward. So people have talked about today many different types of molecular payloads they might like and different types of bioimaging processes. And it's often a combination of things that make a product work. Whether you'd like to have a drug and a tracking agent on the exterior of a particle, you'd probably like to have those into tune ratios so that you know exactly what you have on your surface. So what we attempted to do was a bunch of different ratios using two different functionalization groups, one with a thiol terminal end and one with a carboxylic acid terminal end. And these were the ratios we attempted to perform. And what we found out is that by adding all of these reagents in a one-pot reaction in a mole ratio as listed here, we could achieve loading that did follow a trend and did match our expectations pretty closely. So you see that the 100% thiol did produce a response as we'd seen before, but then when we dropped that percentage of the mole ratio down to 75 thiol, 25% carboxylic acid, that also dropped as well. And then the 50-50 also showed the same trend there. So we're able to really nicely tune and reproduce these results batch to batch, which was really exciting. Now, to further give some quantitative results to this, we performed high-resolution X-ray photoelectron spectroscopy and found that when we had a adventitious carbon peak in each of these samples, we could compare the amount of functional groups on the surface based on the bonds that were in the functional groups. And we found that these actually really matched the results from the Ellman's assay results as well too, and further helped us quantify the loading on the surface. And we found that the results were pretty close to 50-50 and then 100% each on the other ends. So those were great findings that helped us further quantify our loading. And just to give you a visual demonstration of what these particles look like under electron microscopy, some STEM imaging was done, and you can see that the iron is in the core, the silica layers on the exterior, and then the sulfur from those thiol terminated groups is dispersed pretty nicely around. And we can also see representative peaks in the energy dispersive X-ray spectroscopy as well that match what we were expecting. So in summary of what I presented here today, I just want to showcase that nanoparticles may require specific surface chemistry for their intended applications, and it would be really nice to be able to tune those in a specific way to meet the outcome that is desired. And the use of microwave radiation really sped up our reaction process and made this much more efficient and much more easy to scale up in the future. However, characterization is a really important quality control factor, and that's something that was often missing in previous studies, so we showcased our ability to use an assay in combination with XPS to determine those results. And these chemistries in the future, we would love to see them extended to other nanoparticles and other surface types, and that's one thing that can kind of join our connection with the Nanomedicine network and hopefully allow those future surface loadings to be viable. And I'd just like to say thank you to the research group and members who contributed, and I'd also like to invite you to connect with us. My contact information here and my former supervisors. As a recent graduate, I'd love to chat with you about future opportunities to work together, and have also provided my LinkedIn QR code. And then I'll take any questions. I'm just gonna put that one back. Yeah, so we were taking a look at that through dynamic light scattering measurements, because that was one approach that we thought could happen, but it doesn't seem that that is majorly happening. The distance in between the particles is pretty well dispersed, and they disperse well in the solution that we have them in. We have them in an isopropyl alcohol, and they disperse pretty readily in that. And they are stable for a couple of days before they start crashing out, but likely due to their size, we haven't been able to confirm whether or not they're having some dimerization or not yet, though. But it is a little challenging once the functional group has been added to figure that out.
Over there?
Just curious if you tried different microwave settings, because I know that makes a huge difference.
Yeah, so we have one that we got for free in like 2003, so it's really not doing well, but it doesn't have any stirring features built into it, which makes keeping that reaction mixture homogeneous and well mixed really difficult. So we're just relying on the microwave process to drive the mixing of that reaction. But there are new microwaves available, and we were able to test one that have built-in stirring features and a built-in thermal camera to determine the exact temperature of your solution. And we think that could be a great way to improve the efficiency of this reaction and drive more onto the particle surface, because right now we're at about 15% loading, so it'd be nice to increase that further. Yeah?
We have the nanoparticles coated with
Mm-hmm.
So does it biodegrade inside water?
No, so the silica is pretty stable actually long-term in alcoholic and also in aqueous mediums. Like, it's pretty robust once it's been formed. So that's makes it a great candidate for future bio applications as well. And it is really stable long-term. And since it's thin, it prevents the the properties of the particles in the middle from being lost. But when you directly attach functional groups onto the surface of iron oxide specifically, it can actually cause leaching of the core material and iron to disperse out of the particle, which then ruins the assembly. So you really do need a protective coating on the outside for these to work as they do.
One more question?
Yeah, so you have actually an example that part when you comment on how they distribute, how they homogeneously distribute spatially or
Well, they both were similar, their same carbon chain length, alcohol-terminated functional groups. We were hypothesizing that they load on, since we found that the ratios were what we expected, so when we had a 50-50 mole ratio in the pot and we reacted it, we found about a 50-50 loading on the nanoparticle surface. The distribution of said functional groups hasn't been determined yet, because that is really challenging. But based on previous studies with attaching gold to those sulfur exterior, which we have done for some of these particles, it does still look pretty uniform. Although it is possible that clusters of one type could be forming, and it won't be just exactly 1, 1, 1, 1, 1.